Welcome to Thought Frontier.
Welcome to our deep dive into dark matter. It's one of the universe's biggest mysteries.
Absolutely. And we're going to try to unpack it today.
We've got two pretty different sources to work with: a scientific paper from way back in 2010, and then a space.com article that talks about neutron stars.
You might be surprised how those two things connect.
Yeah, I'm curious to see how this plays out. But before we get too deep into the weeds, maybe we could start with, what exactly is dark matter? I mean, it's not like we can see it, right?
Yeah, that's the thing. It doesn't emit light or reflect it, so we can't see it directly. That's why it's called dark. But we know it's there because of the way it affects things we can see.
Okay, so how did we even figure out that this invisible stuff exists in the first place?
It all started back in the 1930s with astronomers like Jan Oort and Fritz Zwicky. They were looking at galaxies and noticed something strange. The stars were moving way faster than they should have been based on the amount of matter we could see.
So it's like they should have been flung out of the galaxy.
Exactly. Just like a merry-go-round spinning too fast. But they weren't flying off. Something was holding them in place.
Some invisible force, huh?
Exactly. Then in the 70s, Vera Rubin really nailed this down by studying galaxy rotation curves in detail. She found that the rotation speeds didn't slow down the farther you got from the center of the galaxy, which is what you'd expect if gravity was only coming from the visible stuff.
Huh. So stars acting strangely was our first clue. But it's not just single galaxies, right? It affects whole groups of galaxies, too.
Right. We see that with gravitational lensing. It's like, well, imagine a bowling ball on a trampoline warping the fabric around it. A massive galaxy cluster does the same thing to space-time, bending the light coming from behind it. And when astronomers measure this bending to calculate the cluster's mass, it's much, much greater than what the visible galaxies and gas can account for.
So like a cosmic optical illusion telling us there's way more out there than we can see. But wait, couldn't this extra mass just be normal stuff that's hard to detect? Like black holes or really faint stars, maybe rogue planets?
That's what scientists initially thought. They called these potential culprits MACHOs, massive compact halo objects. The idea was that they might be hiding out in the halos of galaxies, providing that extra gravity.
So how did they test that? Was it like a cosmic game of hide and seek?
Pretty much. They used something called microlensing surveys. It's where you look for tiny changes in the brightness of distant stars, which would happen if a macho passed in front, bending the light with its gravity. They did find some microlensing events, but not nearly enough to account for all that missing mass.
So it's not just normal matter hiding in the dark. We're talking about something totally different. Something darker.
And here's another piece of the puzzle. When we look back at the very early universe, we can estimate how much regular matter should exist based on things like the Big Bang Nucleosynthesis and the cosmic microwave background radiation.
Right, the afterglow of the Big Bang.
Yeah, and guess what? The amount of normal matter we can account for is way less than what's needed to explain the gravitational effects we're seeing today.
So it's not just missing matter. It's missing matter that isn't even the kind of matter we're used to. Does this bring us to particle physics?
You got it. The leading theory is that dark matter is made up of something called WIMPs.
WIMPs. Okay, I gotta ask. What does that stand for?
Weakly interacting massive particles.
So it's not interacting much, but it's massive. Does that mean it's heavy?
Massive, in this case, refers to having mass, which means it exerts gravity. So yeah, you could say it's heavy in a way. But here's the cool part. This WIMP idea, it actually fits into some bigger ideas in physics.
Oh, you mean beyond just explaining this dark matter thing?
Right. Our current understanding of particle physics, the standard model, is really successful, but there are some things it doesn't explain perfectly. WIMPs could actually help solve some of those problems.
Okay, this is getting good. Lay it on me. What kind of problems?
Well, for one, the standard model doesn't quite explain things like gravity at the quantum level or why neutrinos have mass. But there are theories that go beyond the standard model, and some of them predict particles that would behave just like what we expect from dark matter.
So dark matter might not just be some weird thing out there on its own. It could be connected to some fundamental stuff about how the universe works at the smallest level.
Exactly.
So which of these beyond the standard model theories is the one everyone's talking about?
It's called supersymmetry.
Let's break this down. What's so super about it?
Well, it's a bit complex, but basically proposes that every known particle in the standard model has a superpartner particle. And some of these superpartners would have the exact properties we need for dark matter. They wouldn't interact much with regular matter, and they could have the mass to explain the gravitational effects we see.
Okay, so it's giving us these potential dark matter particles. But how do we go from a theory to figuring out exactly how much dark matter should be out there?
That's where the Big Bang comes in. Physicists can use the Big Bang model and what we know about thermodynamics to kind of rewind the clock back to the very beginning, when the universe was extremely hot and dense.
Like a giant cosmic pressure cooker.
Yeah. Imagine particles constantly colliding and even annihilating each other. As the universe expanded and cooled down, these collisions became less frequent. Eventually, particles stopped interacting so much and froze out, kind of like a game of musical chairs where some particles are left standing when the music stops.
I'm starting to see where you're going with this. The particles that don't interact much, like our WIMPs, would be more likely to survive.
Exactly. It's like survival of the weakest in the early universe. And here's the amazing thing. When physicists calculate how much dark matter should have been left over from this freeze-out process, it matches remarkably well with the amount we actually observe in the universe today.
Wow. So we've got a theory that not only explains what dark matter could be, but also predicts the right amount of it. That's pretty convincing.
It's a beautiful example of how theoretical physics and cosmological observations can come together to create a really compelling picture. But there's a catch.
What's the catch?
We still haven't actually detected any of these elusive WIMPs directly. It's a lot harder than just looking through a telescope.
So the hunt is on. In part 2, I'm guessing you're going to tell us how scientists are trying to catch these cosmic ghosts.
You bet. It's a story that's still unfolding, and it involves some pretty incredible science.
Can't wait. All right, so last time we left off with this big cliffhanger. Scientists are trying to catch these WIMPs, right? But if they're so weakly interacting, how do they even go about doing that?
Well, it's not easy, that's for sure. But there are some incredibly clever experiments out there. And they basically fall into two main categories: direct detection and indirect detection.
Okay, 2 approaches. Let's start with direct detection. What's that all about?
So direct detection is like trying to catch a WIMP red-handed, so to speak. You set up a super-sensitive detector, often deep underground to shield it from background noise, and you wait patiently for a WIMP to bump into an atomic nucleus.
Okay, so kind of like a cosmic billiards game.
Yeah, sort of, except the cue ball is invisible and weighs next to nothing.
And when this tiny, invisible cue ball hits, what happens? Do the detectors explode?
Not quite. We're talking about incredibly tiny recoils when a WIMP interacts, like a bowling ball hitting a pin. But on a microscopic scale, it takes incredibly sensitive equipment to even register these events.
Makes sense that these experiments would be underground then. Got to block out all that cosmic noise. So, have any of these detectors actually seen a WIMP?
Well, that's the million-dollar question. No definitive WIMP signal yet, but they have ruled out a lot of possibilities. Each experiment helps us narrow down the range of masses and interaction strengths that WIMPs could have. It's a process of elimination.
So even a null result tells us something. What about the other approach, indirect detection?
Right, so indirect detection is all about looking for the byproducts of dark matter annihilation, kind of like looking for the smoke from a fire you can't see directly.
So we're not trying to catch the WIMP itself, we're looking for evidence that it was there.
Exactly. And there are several different signals we can look for. One of the most exciting is gamma rays.
Gamma rays, huh? Those are pretty high energy, right?
Yep, the most energetic form of light. And there are places in the universe, like the center of our galaxy, where dark matter is thought to be super concentrated. If WIMPs are annihilating each other there, they could produce a detectable gamma ray signal.
So telescopes pointed at the galactic center, waiting to catch a glimpse of those gamma rays. Has anything turned up?
Well, there have been some interesting hints, but it's not conclusive.
How so?
The problem is that there are other things out there that can also produce gamma rays, like pulsars and supernova remnants. So disentangling a potential dark matter signal from all that background noise is a huge challenge.
Sounds tricky. So it's like trying to hear a whisper in a hurricane. What about those neutrinos? Last time you mentioned that scientists are looking for those coming from the sun.
Right. The idea is that if WIMPs exist, they could be captured by the sun's gravity and accumulate at the core. And as they bump into each other there, some of them might annihilate and produce neutrinos.
Neutrinos. Aren't those notoriously hard to detect? I mean, they barely interact with anything.
They are. That's why we need these giant detectors like IceCube in Antarctica and Super Kamiokande in Japan to have any chance of catching them.
Anna, any luck so far?
No smoking gun, unfortunately. But these experiments have been able to set some pretty tight limits on the properties of WIMPs, which helps us refine the search even further.
So even when we don't find something, we're still learning.
Exactly. It's all part of the process. But even with all these incredible experiments looking for WIMPs, there are still some scientists who think we might be barking up the wrong tree entirely.
Oh, really? What did they say?
Well, there's this alternative theory called MOND, which stands for Modified Newtonian Dynamics. It's pretty radical. It basically says that we don't need dark matter at all to explain those weird galaxy rotation curves we talked about.
Hold on, are you telling me we might be able to explain all this without any invisible particles at all?
Some scientists think so. MOND proposes that our understanding of gravity needs a little tweaking, especially at those extremely low accelerations we see in the outskirts of galaxies. It introduces this new constant that kicks in when gravity gets super weak.
So like a cosmic cheat code for gravity. Does it actually work?
Well, it can explain some of the observations, at least on galactic scales. In fact, it can fit the rotation curves of certain galaxies surprisingly well, just by adjusting the gravitational force. It even makes some accurate predictions about how galaxies with different surface brightnesses behave differently.
It sounds pretty compelling. But I'm guessing there's a catch.
There is. While MNAD might work okay on galaxy scales, it runs into problems when we look at larger structures, like galaxy clusters. Remember the bullet cluster we talked about earlier? The way gravity seems to be separated from the visible matter in that collision, that's really hard to explain with MNAD.
So it's like a patch that only works on some parts of the universe, but not others.
Pretty much. And another problem is that experiments here on Earth, even those that can measure things at super low accelerations, haven't found any deviations from Newton's laws. So if MNAD is right, it would have to be somehow switching on only in certain astrophysical environments, which seems a bit too convenient for most scientists.
So MNAD might be an interesting idea, but it's not really a slam dunk.
Yeah, most cosmologists agree that it's probably not the whole story. So for now, dark matter still reigns supreme.
Okay, back to our WIMPs then. But even with dark matter as our leading contender, there are still some things that don't quite add up, right?
Absolutely. There are still some puzzles that keep cosmologists up at night. And that's where we'll pick things up in part 3.
Welcome back to our deep dive. We've covered so much ground already. It's amazing to think about how far we've come in our understanding of dark matter.
It really is. From those early hints that something was off with the way galaxies rotate to these cutting-edge experiments trying to directly detect WIMPs, the progress has been remarkable.
And the thing is, even if we never find a single WIMP, the search itself is teaching us so much about the universe.
Exactly. I mean, we're talking about fundamental questions here about the nature of matter, the evolution of the cosmos, the basic laws of physics. It's mind-blowing.
It really is. And it's a reminder that there's still so much out there that we don't understand.
That's what makes it so exciting.
Okay, but I know some people listening might be thinking, so what? Why should I care about dark matter? It's not like it's going to affect my daily life, right?
Well, on the surface, maybe not. But, it's not really about whether dark matter will help us pay our bills or get us to work on time. It's about something bigger.
Okay, I'm listening.
It's about expanding the frontiers of human knowledge. It's about figuring out what the universe is made of and how it all works. It's about pushing the boundaries of science and exploring the unknown.
I like the way you put that. And who knows, maybe someday this knowledge will have practical applications.
Exactly. I mean, look at the history of science. So many discoveries that seemed purely theoretical at first ended up leading to incredible technological breakthroughs.
Yeah, like electricity. Who would have thought that messing around with wires and magnets would lead to the entire digital age?
Exactly. So even if we can't see any immediate practical applications for dark matter research, history tells us that it's worth pursuing knowledge for its own sake.
Absolutely. And who knows what amazing technologies or insights might come out of it down the road. Okay, before we wrap up, I think it's time to leave our listeners with something to really chew on.
You mean a final thought-provoking question?
You got it. So we've been talking about dark matter as this mysterious substance that makes up most of the matter in the universe. But what if that's just the beginning?
What if there's more to it than that?
Exactly. What if dark matter isn't just a single type of particle? What if there's an entire dark sector out there, a hidden world of dark matter particles that interact with each other through forces we can't even imagine?
It's a pretty wild idea.
It is. Could there be dark stars, dark planets, even dark life existing in this parallel realm completely invisible to us? It's mind-blowing to think about.
It really is. And the craziest part is we have no idea what we might find if we could peer into this dark sector.
It's a whole new universe of possibilities just waiting to be explored.
And that's the beauty of science. There's always more to discover, more to learn, more mysteries to unravel.
So the next time you look up at the night sky, remember that what you see is just a tiny fraction of what's actually out there.
Keep exploring, keep asking questions, and never lose that sense of wonder.
Well said. Thanks for joining us on this incredible journey into the world of dark matter.
Until next time.